All right, this is the last video for section 7.1. I mentioned we're learning about a few other sort of random things that are related to angles that we're not going to use terribly often in this chapter, but that are important nonetheless. So we're taking the opportunity now to do it here at the beginning. So the application here is speed. When you're talking about circular motion, so whether it's you're spinning something around on a string, or you've got objects going around in a circle, like maybe the moon going around the Earth, although that's technically an ellipse, but sometimes it's like a circle. Or maybe it's other circular motion, like maybe it is the tip, like a point on a wheel going around, or like a gear moving around. Perhaps it is a Ferris wheel, or like a, what's it called, with the horses that go up and down. You know that thing with the horses that go up and down. My son likes to ride on those. So whenever you have something moving around in a circle, okay, let's say we're just going to think of it basically as a point moving around in a circle, and then here is the center of the circle. If for a certain span of time, okay, so time passed is going to equal t. Okay, we're going to use lowercase t to represent the amount of time that's gone by. During one period of time, this thing is going to move some distance. So let's say it moves like that to over here. Okay, we're assuming this is like constant regular circular motion. So it's moving at a constant speed in a circle. So that distance there, the distance it moves is s, the arc length, right? And then as it moves, it is going to trace out, like the ray from the center of the circle out to the position of that object traces out an angle. That angle is theta. There's two different types of speed that you can calculate here. One type of speed is angular speed. Angular speed, or angular velocity sometimes, especially in a physics class, angular speed is represented by the Greek letter omega, which basically looks like a curly W. That's an omega. Okay, so that is our angular speed, and that's basically how much angle is swept out by the ray. How much angle does this object move through during that period of time? So it's the rate of change in the angle with respect to time. It's theta divided by t. All right. So there's one formula. Our angular speed is theta divided by t. The other type of speed is linear speed, and linear speed is like how fast is the object actually moving around the circle. When you talk about speed, generally this is the type of speed you mean. Like, how fast is it going? How much distance does it travel through? Divided by the amount of time. So that one is represented by the letter v for velocity, and that's going to be s divided by t, where s is the arc length. So since s is the arc length, we actually already have a formula for arc length. We, in the previous video, learned that arc length is r times theta, right? So that's r theta over t, which means that this is r times theta over t. Like that, we could write it as r times theta over t, and theta over t is omega. So what this means is actually taking these two pieces of information and like putting them together. The linear speed v is related to the angular speed by just multiplying by the radius. So v equals r omega, and that is the equation that relates these two types of speed to one another. So let's do an example where we have to use this stuff. In this example, heads up, this example is going to involve a lot of unit conversion. So get ready for your unit conversion. Let's talk about a wheel on a car. A wheel of radius 10 inches, which I looked it up, and 10 inches is this is including the wheel and the tire. So it's the total like radius of the wheel that's, in contact with the road. A wheel of radius 10 inches is rotating at, let's say, a constant 9.8 revolutions per second. So this is the number of times it goes around. A revolution is like a full circle. You could also say rotations per second. They're kind of synonymous in this context. So 9.8 revolutions per second. Let's find the linear speed and measure that in miles per hour. Okay. So basically, we're revolutions per second, that's how many times the wheel is going around every second. And if the car is driving, the wheel here is in contact with the road, okay? And if there's no slipping between the tire and the road, then the like linear speed of the a point on the outside of that tire is equal to the speed at which the car is traveling horizontally. Okay, because the amount of like distance covered around the arc of the circle is going to be equal to the amount of distance covered along the ground as the car is moving, right, as it's rolling. So what we're really calculating is how fast is this car driving, okay? So let's start with this information. Let's start with the fact that the radius is 10 inches. So r equals 10 inches. All right, the fact that I want this to be in miles per hour, I'm going to first go ahead and convert this to, hang on a second, let me think about that. Let's go ahead and convert that to feet. 10 inches is going to be 10 inches, divided by times 1 foot divided by 12 inches. There we go, that's what I meant to write. 10 inches times 1 foot per 12 inches. So this inches will cancel out here. We'll get 10 over 12 feet. Let's use that. We're going to use 10 over 12 feet as our radius. Now the other piece of information, this 9.8 revolutions per second, this is omega. This is a measurement of angular speed, right? How fast is the thing going around? How fast is the angle changing? How fast is the wheel rotating? Right? That's an angular speed. So if I write omega equals 9.8 revolutions per second, what we can do here is we can convert this into radians. We need this to be in radians per something, because in order for all these things to work out, and in order for us to use this formula, this theta must be in radians. Okay, I said this in the previous video as well. If you're going to use the arc length formula, S equals R theta, theta has got to be in radians. So since that arc length formula is what this formula relies on, right? We used it to kind of establish this formula. We have to have our omega measured in radians per something, whether it's radians per second or radians per minute. We don't care, as long as theta is radians. So revolutions will not do. What we can do is multiply by a conversion factor. We know that 1 full revolution around the circle is equal to 2 pi radians. So we put 1 revolution in the denominator and 2 pi radians in the numerator. Revolutions cancels out, and we have 2 pi radians per second times the 9.8. And so this is exactly 16.3 repeated times pi. Oh, nope, sorry, that is the wrong piece of information. Nope, I was reading the wrong part of my notes. We'll just use this. It's 9.8 times 2 pi radians per second. Okay, so now it's time to do, we've got our R, we've got our omega. Now we can use this formula. So V equals R omega. Let's do that. V equals R omega. So that's going to be 10 over 12 feet times 9.8 times 2 pi, and that's in radians per second. So then now multiply those together, 10 over 12 times 9.8 times 2 pi, and this is going to be 16.3 repeated. And the units, because radians are technically unitless, the radians aren't going to be part of our answer. Those are technically, like, they're not a real unit, right? They don't really count as being there. The only units we're going to have is feet in the numerator, seconds in the denominator. So we've converted this to feet per second. And there we go. We've calculated the speed of the car, but that's in feet per second, all right? So there we go. So now, if we want this in miles per hour, we have to do one more unit conversion. So 16. Oh, I forgot the pi. Oh, I'm sorry. I got distracted. This is supposed to be a pi right here. This is times pi. So 16.3 repeated times pi feet per second. If I want to convert that to miles per hour, I just have to multiply this by a few different things. First of all, let's get the feet and convert that to miles. We have 5,280 feet in 1 mile. That's just something my brain remembers. If you don't remember that, look it up. You can just Google it. Number of feet in a mile, right? So there's that conversion. And then if we want to convert seconds into hours, we have to do, well, 60 seconds per 1 minute. Thank you, Babylonians. Times 60 minutes per 1 hour. So we've got to take 16.3 repeated times pi, divided by 5,280, and then times 60, and then times 60 again. And that, multiply that all together, and that's approximately 35. And now feet cancel with feet to give me miles. Seconds cancel with seconds. Minutes cancel with minutes. And I have 35 miles per hour, approximately. There we go.